Last time we were looking at curves, polygons, and symmetry. We're about halfway through, and I believe we had just, well, maybe about halfway through even, talking about quadrilaterals. Does that sound right? We had talked about which quadrilaterals so far? Trapezoids and parallelograms and rhombus. And I think that's where we stopped, right? Okay. We have a few more. The next two are related. Again, that's why they're kind of joined on the same slide. A rectangle is a parallelogram with a right angle. And then a square is an equilateral rectangle. So some people get really bothered by the fact that we're going to very clearly say that a square is also a rectangle. So down here, this one is a rectangle. That is our most specific name for it. What other names does it actually have? Yep, it's a quadrilateral. What else? There's two other names we could give this shape. Not a rhombus. What makes it not a rhombus? It's not equilateral. The two segments on the top and the bottom are longer, so it's not a rhombus. It technically will be a trapezoid because a trapezoid will have either one pair or two pair of parallel sides. So that works. There's one more thing. It's a parallelogram because it has two pair of parallel sides. Okay, but rectangle is the most specific name for it, right? But it is those other things too. And then this one, the most specific name for the one on the right is a square. But again, not only is it a square, it's also a rectangle and a parallelogram and a trapezoid. And this one, Madison, is a rhombus because it does have all four sides equal. It is equilateral. Okay, so we could write all those names associated with this one and they would be correct. But most specifically, it's a square. All right, this is our last quadrilateral shape that we're going to talk about. This is a kite. A kite is a quadrilateral with two adjacent sides congruent and the other two adjacent sides also congruent. So you'll see the little markers. The picture on the left is probably the one that you sort of think about the most frequently if you see or hear the word kite. Yeah? They even drew the sort of cross sections in between the diagonals. You have the two sides on the far left. They've got the one hash marks on them. Those are congruent because they've got one hash mark. And then the two sides on the left are congruent because they've got the two hash marks on them. So subsequent sides have to be congruent in pairs for it to be a kite. So if you're looking at the other two diagrams, they aren't marked, but these are the sides that they're saying congruent here for it to be a kite, obviously, and these two as well. Now, last time we encountered this sort of arrow shape, we looked at it from a hexagon perspective. I can't remember who drew that for us, but this kind of an arrow shape is also a kite by definition. It's not the one you think of when you think of kite, right? But it is, because these two sides are congruent, and these two sides are congruent. Okay? Now, is it concave or convex? Which one?
No, concave.
This one's concave, right? Because I could draw a line segment that connected two pieces of it and it goes outside the figure. So this one is a concave shape. But the definition doesn't require that it be convex for this to work. All right? So that would also be considered a kite. All right, so we're going to do a few true-false statements. We'll do them together. The first question says, true or false, an equilateral triangle is isosceles. This one's true. Yeah. Isosceles just means two equilateral sides, but it's not two and only two. Okay? So isosceles means there's two, and an equilateral triangle has two congruent sides. So this is a true statement.
Wait, does an equilateral have three?
It does, but it's
So
three.
it's three, okay.
But three includes
Three includes two.
two.
Okay.
Yeah, yeah.
Okay.
You have to be really careful with mathematics because sometimes we'll describe things and we'll say it's exactly two. So if isosceles said exactly two,
Okay.
then it wouldn't work, but that's not the definition for isosceles. Yeah. How about B? A square is a regular quadrilateral. There's two words there to consider, right? First of all, is it a quadrilateral?
Yes.
Yes. Do you remember what the word regular means? Flip back in your notes. I know it was last time and you probably haven't thought about it for a couple days. What did regular mean? Okay, equiangular and equilateral. Is a square equiangular?
Yes.
Yes, 4 right angles. Is it equilateral?
Yes.
Yes. So is it regular?
Yes.
Yes. So is a square a regular quadrilateral?
Yes.
Yes, it is. So this one's true. As a matter of fact, when we talked about regular, that's the one that I told you is the most common regular quadrilateral regular polygon rather, that you see sort of in your mind when you're thinking about something that fits those descriptions, equilateral, equiangular. All right, square is a rhombus with a right angle. So there's two pieces here, right? The fact that it's rhombus and the fact that it has a right angle. So is a square a rhombus? Yes, because it has 4 equal sides, right? 4 congruent sides. Does it have a right angle?
Yes.
Yes. So is this true or false?
True.
Also true. D, all angles of a rectangle are right angles. True. Now notice that's not the definition of rectangle, was it? What did the definition of rectangle say?
It's just a parallelogram with
Yeah, it says a parallelogram with a right angle. It just says a.
But if all of the sides are equal and there's a right angle, then it has all of it.
Right. So we could actually use some geometry proofs or definitions and theorems and so forth, and we could actually prove that that's enough to show us that they really do have all 4 right angles. It's a true statement. So this one's also true. E, a rectangle is an isosceles trapezoid. So there's 2 pieces here, right? Okay, so is a rectangle a trapezoid?
Yes.
Yes. Because it has at least one set of parallel sides, and a rectangle has 2, right? Is it isosceles?
Because it has 2 congruent.
Yes.
Yeah, okay.
Isosceles means 2 sides are congruent, and actually in a rectangle,
They're all 4.
both pairs are congruent. They don't have to all 4 be congruent to each other.
Of them, but yeah.
Yeah, but there's 2 pairs, right?
Right.
Yeah. So this one's true. All right, now when we have the word sum, it means that it doesn't have to be true all the time, but just like there exists one that works. So be careful on the sum versus, all. Some isosceles trapezoids are kites. Okay, so isosceles trapezoid means you have 2 sides and they're opposite sides. The 2 opposite sides are congruent, okay? And for it to be a trapezoid, it means that you have at least one pair of parallel sides. This actually is true. Do you know what shape it would have to be to actually fit those descriptions? So if you go back to our pictures of kites, actually none of these pictures fit the description, right? None of these ones actually do. Okay, so basically what I'm asking is we need a trapezoid picture and a kite picture that fit both descriptions. We need a trapezoid that has consecutive sides congruent. Okay, so if it's a trapezoid, we know that two opposite sides, yes, this is an isosceles trapezoid. 2 opposite sides have to be congruent. And if it's a kite, 2 consecutive sides have to be congruent. So what does it tell you has to happen about all your sides?
All 4 sides.
They would have to all 4 be congruent. Do you have a shape that has all 4 congruent? A square or
Oh, wait, not a rectangle.
not a rectangle?
Sorry.
A rhombus. So more generally a rhombus, although a square certainly is a rhombus, right? So in order for this to be true, it has to be a rhombus. And by default, it could be a square as well, right? So this would be true, and the shape that you'd be looking at is a rhombus shape. Does it have to always be true? No.
So a rhombus can be a kite?
Yeah.
Yes.
That's crazy.
Yes. We're going to draw a wonderful picture here in a moment to actually talk more about that fact. But yes, a rhombus is a kite. Not just can be, it actually is one. Yeah, we haven't related those two together yet, so that's why you're thinking, did she say that? No, the answer is no, I didn't say it yet. All right, one more, last one, G. If a kite has a right angle, then it must be a square.
Well, yeah, because what we just said, if
Oh, yes, then yes, because it's a rhombus. No? It's false. It's false.
If a kite has a right angle, then it must be a square.
It's false. I'm thinking it's false. It's false. But watch it be true. It's going to be true. It's
Still,
true.
if you have right angle, that's
Is it
gonna
both?
affect the sides and the
I'm
offset.
thinking,
Like,
Okay, so let's draw some pictures. I don't have a picture in mind because I thought I could wing it, but I'm having a hard time with my picture in my head to draw for you, so let's see if we can figure it out together. So we need a right angle, and we need this, right? We need sides that are parallel to the two that I just drew. No, we don't, because this isn't a parallelogram. We need a side opposite one of these that's congruent to it, though, correct? Okay, we do need that. So we need at least one of these, and I didn't mean to necessarily draw them the same length. Let me draw one of them a little bit longer, just for the sake of fun. There we go. All right, so which one do you want to have a congruent side to the one that I just drew? The shorter one? Okay, so this the shorter one that I have drawn has to have a side that's congruent to it. And we want to draw it in such a way that we're convinced that it's not a square. So that's why I drew the other side longer, okay? And our goal is to see whether or not this will work. So I need this then. It would be something like that, right? Okay. Or if I drew it like this, that'd be okay too. I still don't have a square, correct? Okay. And then either of those, well, actually, let me make the comment. It can't be this one. What's going to be wrong with this one if I were to try to connect my sides? Why is that not a kite? Yeah, I don't have the opposite sides congruent, right? These two would not be congruent if I did that. Okay. I'm sorry, not those two. These two. That's what I'm supposed to be drawing, right? I didn't draw my first one very right. I'm really struggling. I'm sorry, guys. This is the one I wanted to draw. This is what happens when you don't draw the picture in your notes to begin with. Okay, I need a side right here that's going to make it not a square. How about that? That work? Okay, so I'm supposed to have these two congruent in theory. That's what you told me to draw. Do those two congruent? And I don't want it to be a square, so those two are like that. And the third side's not equal to the other ones because it's supposed to be not a square. Whoopsie. That's what I would get. What's wrong with this shape? Why is this shape not a kite? That's the picture I wanted.
the other adjacent sides are not congruent to each other.
Right. These two are not congruent. Agreed? Okay. So maybe there was a flaw in how I drew it. Maybe it can't be a square, but maybe this side actually is the same length, right? Maybe it's a rhombus, because it certainly could be a rhombus without being a square. Agreed? Okay. So now I've got three sides that are all congruent. That's okay. What's going to happen then when I connect the fourth sides together?
Opposite sides still.
Yeah,
Opposite sides still aren't.
these two are still not going to be congruent, right? It's going to be longer. That fourth side that's sort of arbitrarily drawn in there is going to be longer. So what piece did I actually fail to make this work on? Well, I failed when I created this piece up here at the top. It does in fact have to be at a right angle. Whoops. Like that, right? Okay, so these have to be at right angles. That has to happen. I've got to have a right angle here. And then if I were to connect these two, again, I don't necessarily have to have the third side at the bottom congruent, but again, if I were to try to do this, what would happen with the sides?
Still.
These still aren't congruent, right? Whoops. So we've sort of tried to defy all of the possibilities or tried to draw it in every way possible to make it not a square. And we're failing miserably, right? Yeah. Is there anything that I have failed to consider when I drew my picture that you guys thought of? Did you think of one, Olivia?
I don't know. I just been like wondering why do there have to be two right angles on it?
Well, when I drew it without two right angles, I had a problem. So I went back and I said, okay, well, obviously it had to have at least had another right angle.
Well, why can't it have like one right angle with the short sides and then the long sides meet?
Okay, so you want me to have the right angle. Oops, I can't draw a straight line now today. There's this line tool in here and it's evidently just not going to like me, so I'm going to try and draw it by hand. Okay, so you want me to draw it like this.
Yeah.
Okay.
And make the other sides meet.
Okay, so you want these sides to be congruent. Yeah, I haven't drawn this picture, that's true. Now what?
And then just
Extend those two lines?
send those two lines to meet in the middle.
To meet in the middle, but not as a square, right?
No, make them longer.
How about that?
Yeah.
Does that one work?
That's a kite though.
Wasn't that what we're supposed to be doing?
Yeah.
A kite?
Yeah, okay.
Okay, so does this gives me a right angle at the top. Okay. I think that one works. If a kite has a right angle, then it must be a square. So is this one true then? So this one would be false, and here's our example. So this would be a counterexample. Did we talk about that in here? No, that was my other class. The word counterexample is an example that shows something's false. So we found one. That's what I was wanting to do. I was wanting to create with you all my possibilities, and that's the one I forgot. Thank you, Olivia. However, I think if we changed part G to say it has a right angle between the non-congruent sides, which is how I originally drew it, then it would be a true statement, right?
Right.
Okay. We just need to consider the right angle on the other one. All right, any other questions on this one? Very well done, thank you. All right. This is a fantastic picture, and it's going to take you a couple minutes to draw it, so I tried to copy and paste it into your notes, but that didn't work very well.
Yeah.
Wonderful technology there. So jot this down, and then we'll talk through it and make sure that everybody's clear on the hierarchy of polygons. Careful to give yourself enough space over there in that quadrilateral spot, because there's a lot going on. Okay, so this picture is certainly not of all polygons, right? So it's just triangles and quadrilaterals, the ones we've talked about so far. There's plenty of other shapes that aren't on here, like what? What other types of polygons are not on this diagram? How about an octagon? Is it a polygon? Yeah, that gon on the end kind of tells you, right? Gon in the end. Yep. Octagons and pentagons and decagons. They're all polygons too. This diagram is just supposed to show you a way to think about the relationship between, in particular, quadrilaterals. Okay, so the triangle side should be okay. We've talked about this now both last class period and this class period, that an isosceles is an equilateral. I didn't say that right. An equilateral is an isosceles. I said that right. Okay? So if you're breaking things down, a triangle is either scalene or it's an isosceles. Those are the only two options. And if it's isosceles, it might also be equilateral. So that's triangles. It's kind of a small category. Quadrilaterals is a huge category. Right? It is. It's huge. So if you take a look at the quadrilateral category, if it's a quadrilateral, it could be a trapezoid or a kite. All right? And if it's a trapezoid, it could be a parallelogram, or it could be an isosceles trapezoid. If it's a parallelogram, it could be a rhombus or a rectangle, and a square is both a rhombus and a rectangle. You notice also a square is a kite, and a square is an isosceles trapezoid, and a square is a trapezoid. A square is everything that is above it. So this is a really nice diagram to think about because, and you might even choose to put it on a note card for a test. Because if you start at any location and you say, okay, I've got an isosceles trapezoid. If I have an isosceles trapezoid, what other name does that shape have? Trapezoid and quadrilateral, and you're done. Polygon, I guess you could say that too. Okay, so those are the other names that you could actually call that and be correct. So this diagram is really helpful for those kind of true-false questions like we just did, as saying, this is what I know I have. What other things can I call this object? And that's helpful. Okay, we're going to shift gears a little bit. The title of this section included one more word. What was the last word on the title of 11.2? Symmetry. Symmetry. So we're going to shift to symmetry now. The first type of symmetry we're going to talk about is called line symmetry. Line symmetry is a line which is its own image under a reflection. I don't really like that definition very much. When I think of line symmetry, I think of a line that cuts the object into identical pieces on two sides. And the two sides could be beside each other horizontally, they could be beside each other vertically or at an angle, doesn't matter, okay? But somehow it cuts it so that if you folded it on top of itself, the image would lie exactly on top of itself. So we're going to start with the figure on the right, the rectangle picture, because that's the easiest one. Where could I draw, actually, my pictures here don't match your pictures on your paper. So start with the rectangle. It's in the middle on your paper. Oops. Where could I draw a line that cuts this diagram, you know, sort of in half the way that I've described to you?
Get down the diagonal. Wait. Are you talking about the square or are you talking about
I was going to do the rectangle first.
Okay. I mean, you could cut it in half and make it two squares.
Okay, so like this, right? If I drew a line through there, I wanted it to be a different color. I'm sorry, just a sec. Well, there's only so many colors that work with both my dark backdrop and my light image. That one will work. That, if I folded my image up along that side, it would lie exactly on top of itself, so at least if I drew the line well, correct? Yeah. Okay, is there another line that would do that? Where is it? Long ways. Same thing, but through the middle horizontally, correct? So the question is, at least in part, how many lines of symmetry would a rectangle have then? It would have two.
Could you cut it across them?
This is a good question. So if I tried to do along the diagonals, is what Morgan's asking, what would happen?
It could not
It won't be.
Yeah, it'll actually fold so that the long piece, it's hard to picture it, I think, a little bit. But if we do it with a piece of paper, if I folded it along here, then what would actually happen is that this piece, I'm going to do it. Okay, so whoever's paper this was is going to be like, why is my paper folded? Do you see what happened? This is the diagonal. And did the piece fold down on top of itself? No, it didn't. Okay, so that's it actually for rectangles. This is Paige's paper, so we'll just have to apologize. All right, so that one doesn't work. However, if we go to a square,
That's just, yeah.
what's going to happen for a square? Do we get the same ones as we had for a rectangle? Yes. We do. So we can get this line. That's not it at all. Let's try that again. This line, and we get this line. What else do we get? We can do diagonals on this. And the reason we can is because we have that equilateral feature to it, actually. So how many lines of symmetry do we have for square? We actually get 4. How about the parallelogram shape that's in the center on mine and on the left-hand side of your notes? Yeah, there aren't any, actually. Every time you try and draw them, so if you draw them like horizontally or vertically, the fold will actually flip it. It'll be flipped the other direction because of the shape of the parallelogram. And if you try to do it along the diagonal, the same thing will happen as did for our rectangle. It won't line up on itself either. So this one doesn't have any. So it's completely within the realm of possible that we have no lines of symmetry. And LOS, you'll see abbreviated sometimes like that. Okay? All right, give a chance for example number 4. These are actually in your notes. The question is, how many lines of symmetry do each of them have? So I don't want you to spend too long doing this, but try to draw in the lines of symmetry on each of these 6 shapes and see how many lines of symmetry you believe each picture has. We'll take just a minute or so to try to draw all of them in and make sure everybody has the same number on each one.
The answer infinite?
You can. I don't think any of these do. But yeah, you could have an infinite number. We'll talk about which one does have an infinite number in a minute. It's not a polygon, so.
But it's not one of these.
Not one of those.
Okay.
Nope, not one of these shapes. Maybe you guys will be able to figure out which one it is before we even get there. The first shape, what's that called? A hexagon. How many did you guys get?
6.
It is, this one is 6. So it cuts through opposite sides like that. So that's 3 of them. Where else does it cut through? Yeah, the corners, the vertices. Any other fold will not lie along itself. So there are 6 on this one. What'd you get for the letter A? Just one, right here. How about for the, I would say it's an oval, but it's not even an oval. It looks more like a track, right? What'd you get? I think there's 2 actually on this one. There's going to be a horizontal and a vertical. So you're going to have, I can't draw it for some reason. My pens are not cooperating very well today. Okay, these are not drawn well, but you can pretend like they are. This is 2. How about part D, the one that looks like the letter Z? There aren't any on that one, yeah, that's a 0. Okay, how about our sort of, I don't know, right turn arrow thing going on here? There's 1, where is it? Yeah, it's at the diagonal, it looks like this. And it will work, so that's 1. And our last shape, which is like you're terribly confused, you don't know which way you're going. Just 2? There's actually 4. This shape's very much like a square because it will work along the diagonals. They're not really diagonals, but they would have been the diagonals for a square as well. So we get 4 for this one. Okay, so these are called lines of symmetry. That's not the only kind of symmetry that an object can have. An object could also have something called turn symmetry. That's what your book uses. Most of the books that I've seen before will call it rotational symmetry. This is a figure which, when turning it by some angle less than 360, about a single point, the single point is called the turn center, causes it to match up with the original figure. So in other words, if you could pick it up and you could spin it a little bit, not all the way around to where you started, but you can spin it something less than all the way around, and it lands right back down on top of itself, then that's considered turn symmetry or rotational symmetry. And all of these objects have this, okay? These three right here. And we're going to take them, I don't think we're even going to talk about all of them, but we're going to talk about the first two. The first one is what symbol? Where have you seen that? It's a recycling symbol. So notice that the recycle logo coincides with itself after a rotation of 120 degrees. I'll talk about where that number comes from in a second. So because it works for 120 degrees, we would say that this logo has a 120 degree turn symmetry. However, we could also rotate the logo by another, that's a typo on there, don't write that second number down, this should not say 240. This should say another 120 degrees. Okay, so after we've turned it 120, we could turn it another 120. And if you add 120 together twice, you get 240. So we could also talk about this having a 240 degree turn symmetry. Okay? What's wrong, Morgan?
I forgot a word on the last slide, and then I got confused. Okay.
We'll stop for just a second, go back.
Thanks.
Rotational, less, and original.
Okay.
Those are the words you should have. Okay.
Sorry.
All right, and then we have some 120s. So we have 120, 120. It should have said 120 and then 240. Fix this in here too.
Okay.
Okay, so how do we figure out whether it's the 120, the 240, if it's a 90, or if it's a 75? I mean, how do we do that? Well, the way that we do that is to find the amount of the turn symmetry for a figure. You take 360 degrees, which is turning it all the way around, right? If something turned all the way around, it would be 360 degrees. And you divide that by the number of similar shapes that you see. So if you go back to our recycle symbol, how many similar shapes are there in this object? There's 3. And what is 360 divided by 3? 120, right? And the reason you get 240 is because you can do a 120 again, 240, and it'll work again, okay? So what about this shape? How many similar shapes do you see on this one? The car tire.
6.
It's 6, right? Do you see them? Those 6 sort of triangular shapes, kind of triangular shapes in the tire wheels? Or in the tire, I don't know, in the tire. Hubcap. Yeah. All right, so there's 6 of them. So if you took 360 and divided by 6, you would get 60 degrees. All right, let's figure out what the turn symmetry is for these 3 shapes. What would you have to do on 5? What would be the calculation you'd need to do? I'm starting it for you. 360 divided by what? 5. Do you see 5 similar shapes in that picture? Yeah. And what would you get if you did 360 divided by 5? Sorry, this is, again, evidently when I copied and pasted it, did not paste them in the same order, which is fantastic. Sorry, I'm looking at the star shape. 360 divided by 5, what is that? 72. It is 72. I don't mean 5, I meant 2. Let's try again. Okay, how about, is this a Chevy symbol? Yeah. Okay, what about the Chevy symbol? Is it Ford? Is it Chevy? Something for a car.
Something like that.
I think that first one is like Chevron or something, isn't it?
Okay, you're right.
It's definitely Chevy. Somebody's got one.
You're right.
Okay, so what would we divide this one by? Any thoughts?
I think 2.
Yeah, it is 2. There's actually 2 similar shapes. If you want to think about it, this is sort of the location where it breaks apart the 2 similar shapes. I'm not saying it's a line of symmetry. That's not what I just drew, okay? But it does break this apart into 2 shapes that are similar. If you rotate them, you will have the same shape if you rotate it by 180 degrees. What would I need to divide our last shape by? 6, right. So this one would end up giving me 60 degree turn symmetry. Note, I want you to notice that a figure could have line symmetry, rotational symmetry, both or neither. So it's not like you get one, you get both, or you get one and you can't have the other one. You can have both things in a particular object, but you don't have to, right? So the first one, for example, has rotational symmetry of 72 degrees. The first one does not have any line symmetries at all. That's not true. It has 5 line symmetries on that one. I just about lied to you.
How do you tell if it has it though?
You have to try.
Okay.
Like if I took this line right here and I folded it across that line, wouldn't they match up? Yeah. But the middle one has rotational symmetry and it doesn't. The middle one on my screen. This is the one I was looking at.
Yeah.
Yeah, this one is not a line symmetry, right?
Right.
Because the 2 edges would fold along the center part would be okay, but the 2 edge pieces would not. And the same thing would happen if I tried the other ones. Does the last one have some line symmetries? Sure, it has quite a few line symmetries actually. So, all right. Last type of symmetry is point symmetry. Point symmetry is when a figure has 180-degree rotational symmetry about the turn center. So it's just a specific type of turn symmetry that's 180 degrees. The turn center becomes the midpoint of a line segment through any point in its image. So like if you took the point and you turned it and you took the point where it landed, those 2 values connected together would create a line segment and their center would be the point center of your circle, the midpoint. So all of these shapes, there's not an example here that we need to do. All of these shapes have this point symmetry. All of them, if you spin them around 180 degrees, you will end up back on themselves. Okay? The same image. Now, not all of them are polygons, obviously. In fact, none of these shapes are are polygons. So if you take a look back over here, the middle diagram and the right-hand diagram would have point symmetries because they both could be spun 180 degrees and land on themselves, so to speak, but the one on the left wouldn't. Correct? It would be a sort of an upside-down version of itself. All right, and we will end with symmetries of a circle. A circle has infinitely many lines of symmetry. Was that your question, Olivia, about lines of symmetry, if you can have infinitely many? Yeah. And you can. You can have a circle, each of which passes through the center of the circle. So if you have a line that is passing through the center of the circle, what is that otherwise known as? At least the line segment that it would create. A diameter. So every diameter of this circle, and there are infinitely many diameters, would be a line of symmetry for a circle. All of the circle's lines of symmetry intersect at the circle's center. The circle also has infinitely many turn symmetries, right? You just rotate it a little bit. You get the same thing over and over again. And it also has point symmetry. It just has so much going for it. All of these different types of symmetry. Circles are wonderful. Okay.